recording if you'd like. Okay, thank you everyone for joining. Happy 2022. I hope everyone had relaxing holidays, or I guess as relaxing as they could be given the usual world circumstances, yada, yada, yada. But we're very excited to continue our series of talks with the first talk of 2022, or talks of 2022, by Scott Melville and Irene Valenzuela, who will be telling us about effective field theories and Swampland. So we're happy to, or I should say actually first just a basic housekeeping. The usual rules for questions are what they've always been. So if anyone has sort of brief clarifying questions during the speaker's talks, we'd ask you to put those in the Zoom chat or in the Slack channel. The organizers will be sort of keeping their eyes on those, and then I'll relay those to the speakers. Any longer discussion-based questions you should save for the Q&A for both speakers after both talks. But with that out of the way, let me go ahead and introduce our first speaker, who's Scott Melville, visiting us virtually from the University of Cambridge, who'll be telling us about signs of quantum gravity at low energies through the effective field theory approach. So Scott, take it away. Thanks very much.
Fantastic. Thanks, Sebastian. And thank you all for coming along this afternoon or this morning, wherever you are. Thank you to the organizers for inviting me. Today, I want to talk to you about a question, which I think is a very basic question, but it's really at the heart of why quantum gravity is so hard. And that is, what can low energy IR observations really tell us about high energy UV physics? Okay, so this is particularly important for quantum gravity because, I mean, we know that general relativity breaks down near the Planck scale, right? We know that there's some new high energy physics out there. It's just that the Planck scale is so much higher than any energy scale we can probe in the lab. We're sort of destined to only ever have low energy IR data. So it's not like searching for the Higgs boson. I can't just go and build a bigger collider and probe the UV directly. I really need some new kind of strategy. So what I'm going to argue today is that actually in our low energy IR data, there's a lot more information about the underlying UV physics than you might expect. So the natural language for answering these kinds of questions is effective field theory. So the main idea behind effective field theory is to try and construct a complete basis that captures all possible interactions that you could have between your low energy degrees of freedom. Okay, all possible interactions that are compatible with any symmetries that your problem has, and also organized in terms of how large you expect each of them to be. So in gravity, right, the low energy degrees of freedom would be your metric tensor. You want to construct interactions that are invariant under diffeomorphisms. And to decide how large each of these interactions is going to be, right, we do the following. We imagine that every derivative is suppressed by an M Planck. Okay, and that means that when you think in terms of energies, at energies much lower than the Planck mass, all of these interactions are small and you recover GR. Okay, so your complete basis of interactions is going to look like all of the possible scalars you can make from products of the Riemann tensor and its derivatives, multiplied by appropriate powers of M Planck. Okay, and this gives you the most general low energy effective description of gravity, right, which looks like GR plus a series of increasingly small corrections. Each of these interactions is multiplied by some undetermined Eft coefficient. Good, so in this language, every UV complete theory of quantum gravity really corresponds to some infinite dimensional vector in this space. It's just a list of these constant coefficients telling you what all of the corrections to GR at low energies are. Okay, good. So this is the cartoon of theory space. You have all your different quantum gravity approaches. And when you go to low energies, they all flow to GR plus some corrections. And these corrections are captured in these coefficients. Good. So now, more precisely, the question that I want to answer today is, in practice, we don't have a full infinite list of coefficients that we can measure, right? We'd be lucky to measure even the first few of these. So if you only have this kind of partial information about what theory describes our universe, what can you do? right? We are low energy people that live at the bottom of this RG flow. And so we can measure the first one or two of these coefficients. How do we extrapolate up into the UV and see which quantum theory of gravity is relevant for our universe? Okay, so that's the problem. So before saying any more about quantum gravity, I want to start with a historical example. Okay? And this is maybe just the most famous application of effective field theory in all of particle physics. And that's Fermi's theory of weak decay. So at very low energies, nuclei can decay by spitting out an electron and a neutrino. And the effective field theory way of understanding this is that you should be writing down all possible interactions between your low energy degrees of freedom. So in this case, quarks inside the nucleus, they can interact with leptons, either electrons or neutrinos. And indeed, the kind of first correction that you would expect is the one that has no derivatives. And an interaction like this is exactly what Fermi wrote down in the 30s. And he showed that this is a really good description at low energies of weak decay. So far, so good. But there's an issue, right? And the issue is that if you take this low energy effective theory and you try and apply it at high energies, you find that everything diverges. Okay, this theory just doesn't make sense. And to combat these theoretical divergences, in the 60s, people realized that you had to add new particles. You had to add some new degree of freedom. And one of the first things they tried was a neutral vector boson, which we now call the Z boson. But I should stress that this was introduced in the 60s on kind of purely theoretical grounds. And it wasn't until the 80s that at CERN, we were really able to collide particles at high enough energies to explicitly see this Z. Okay? The idea in the 60s was that you have some new particle with some mass m. And what that means is when you create one, it'll propagate some characteristic length, which is kind of like 1 over m. So from a low energy point of view, right, if you can't resolve length scales of order 1 over m, this propagating internal guy will just look like a point, and it'll just look like Fermi's contact interaction. So if we were to turn back the clock, right, imagine you were a theorist living in the 70s. This is just one candidate UV theory. Okay, in the 70s, they hadn't measured neutral currents yet. And in fact, there were various models that just didn't postulate them at all. There was other kinds of UV completions, right? Other kinds of new particles, which when you zoom out, look like Fermi's contact interaction. So one example of that is something called a leptoquark, which is when you take a lepton and a quark and you stick them together, right? It's just some exotic composite particle. And they show up a lot in grand unified models. Okay, so there was some reason to think there might be something like this in our universe. And if there was, it would contribute to Fermi's constant. Good. So of course, CERN was able to actually go up to the UV and produce Z bosons. So we know for sure that our universe has Z bosons and not leptoquarks. Right? But this is a good example of the sort of question we want to answer. Imagine you were Fermi in the 30s and CERN was a long way away. All you could measure was this low energy interaction. How could you tell if your universe had Z bosons or leptoquarks? And I think the really amazing thing is that you can tell. I think Fermi could have told you that the universe had Z bosons, right? Even though he couldn't probe those scales directly. And the argument he could have made is the following, right? If you look at these two proposals carefully, if you have some new particle, the Z boson, and it couples to quarks with some strength G, and it couples to leptons with some other strength G prime, then when you zoom out, right, when you go to low energies and you have just this effective contact interaction, that strength has to be the product G times G prime. But if you compare that with what happens in these leptoquark scenarios, right? Leptoquark, this new particle, it couples to quarks and leptons with some strength G. And in this diagram, it's the same coupling that appears in the top and the bottom. So this EFT coupling is G squared. It's always a positive number. But these neutral vector bosons, they can generate Fermi constants that are positive, negative, whatever. So this is the part of the story that just really blew my mind, right? When I first heard about this. In our universe, right? If you measure this coefficient, It's actually about minus 0.1. Right? And so what that tells you is that you couldn't possibly have some leptoquark at high energies mediating this interaction. It doesn't matter how you fiddle with these UV parameters, because you're always going to land on positive Fermi constants, and that's not what's measured. So I should say that at the time in the 30s, right, Fermi only measured the total decay rate. So he knew what the mod square of this number was, right? He didn't actually know its sign. But in principle, he could have done a low energy interference experiment, right, to see whether this thing was positive or negative, and actually would have told him whether it was Z bosons on very small scales mediating this interaction or leptons. So the modern perspective on these kinds of problems, right, goes something like the following. Really what we've done is at low energies, right, our effective field theory has this constant, this parameter, and we've split the low energy parameter space into two regions. Okay, this parameter can either be positive or it's negative. So really what we want to do is organize all possible UV completions also into two categories. Okay, and the way to do this, right, turns out to be to ask the following question. In a given UV completion, right, is it dominated by some spinning particle, a spin greater than 1 in the T channel, right? Yes or no? So for Z bosons, the answer is yes, right? This is a spin 1 thing, it's exchanged in the T channel. For leptoquarks and other kind of related proposals, the answer is no, because you're not exchanging anything in the T channel. Good. So then you can show, like on super general grounds, that any UV theory that lives in this column here, right? So anything that doesn't exchange a vector field in the T channel always gives you a positive Eft coefficient. It doesn't matter how many leptoquarks you have, how ingenious you are with their couplings, whether it's tree level, loop level, whatever, right? You're always going to land on a positive effective field theory constant. And that means that when Fermi did this hypothetical interference experiment, right, measured a minus 0.1, he could have ruled out not just leptoquarks, but really any theory that didn't have some vector or higher spin particle in the T channel. Okay. So this is the logic, really, which is going to kind of underpin the rest of the talk. It goes like follows. What you want to do is find some UV feature, okay, some feature of UV completions, which implies a constraint on your low energy parameter space. What that would mean is if you were to measure any violation of this bound, then that feature in the UV is forbidden. It's just not something that could be realized in our universe. Okay, so in this example, measuring a negative Fermi constant tells you that you need to have some neutral boson in the T channel. Great. So we want to take this story and bring it to quantum gravity. That's really the idea. Wouldn't it be great if we could do the same thing for quantum gravity? Because there, it's really like we're theorists in the 70s again, right? There's all these different UV approaches, right? Here are just some, and they're all very different on small scale. They postulate very different things about the fundamental structure of our universe. But at low energies, they all reduce to GR plus these corrections. These corrections, would show up as small deviations in how the metric interacts with itself and how the metric interacts with matter from the predictions of GR and the standard model. And now you might think that unless you can actually probe energy scales close to M Planck and resolve whatever the new physics mediating this interaction is, then it's hopeless, right? That from these numbers, you're never going to be able to tell exactly which of these UV completions is quantum gravity. But that's not quite true, right? Because in each of these approaches, there's whole ranges of these coefficients that are just forbidden, that you could just never hope to access. Okay, so this is the cartoon of what I'm saying. This is the dream, right? This is really what we would like to have. We would like to be able to say that, if in the UV you had some kind of string theory, then your Eft coefficients have to live in this red island. Right? If it was look quantum gravity, you have to be in the green one. If it was non-commutative geometry, you have to live in the blue one, and so on. Right? We just make a map of what all of the different regions in this parameter space correspond to. And now, if it's not clear immediately why this map would be amazing, let me give you 3 reasons. Okay, reason number 1, why this map would be amazing. It would give you a way to translate low energy measurements of these corrections to GR into something concrete about the UV. So if you measure these coefficients, C1 and C1 prime, and it's kind of in this corner, say, of the red island, you would conclude that this universe could be described by string theory, but not any of these other approaches, right? Which would be huge. Reason number two why this map would be amazing is that it would let you design observables that were maximally discriminating. Okay, so the way I've drawn this cartoon, you can see that measuring C1 prime, for instance, would not be a super good way of distinguishing different quantum gravity theories, right? Because there's a wide range of different values of C1 prime that are all kind of consistent with most of these quantum gravity proposals, right? Really what you would want to measure is something like C1, because there, you know, if you give me some reasonable estimation of C1, it's really going to pin down. You're either in like the green one or the red one or the blue one. The overlaps are much smaller. And then reason number three, and I'll come back to this later in the talk, is that measuring these corrections is very hard. These corrections are very small. And so anything that makes that estimation easier is surely a good thing, right? And one use that you can put these kinds of islands to is improving the constraining power of your data. And the way that that would work is, say someone could make for you a map like this, right? And you would notice, aha, no quantum gravity approach that I can think of generates a negative value of C1 prime or a negative value of C1. It just never seems to happen. So perhaps those effective theories are just sick. They're just secretly unphysical. So now you tell that to your observer friend, right, who has some data and is trying to fit his data using these parameters, right? For him, that's huge news, because now he is trying to fit the same data, but with fewer allowed parameter values. Now he can only use this top quadrant of values of C1 and C1 prime to fit his data. And that inevitably means that his contours are going to shrink. He's going to get a better estimate of these parameters. Fantastic. So that would be the kind of long-term dream, right? And of course, I should say there's been a lot of progress in this direction over the last few years, right? And I think in the next talk, we'll hear a lot more about some of these islands, particularly like the string theory island. The Swampland conjectures is all about working out what the boundary of this island is. But for the rest of today's talk, what I want to explore is this kind of particle physics inspired possibility, which is instead of picking a particular UV approach to quantum gravity, instead, let's just try and sort them. Let's just organize them into two categories. Okay, I want to put on the left all the quantum gravity approaches, which are unitary, causal, and local. I'll define in a moment what I mean precisely by each of these things. Right. So for instance, string theory ticks all these boxes. And I want to put on the right-hand column all of the approaches which violate at least one of these things. Okay, so as far as I'm aware, most discrete approaches violate at least one of these things. And then what we're going to show is that at low energies, right, anything in the left column has to give you a positive effective field theory coefficient at low energies, right? And everything in the right column can really be anywhere, right? It's really the same story we had with the leptoquark and the Z-bosons. Okay, now, so we can use the same logic. We can then go looking for these small corrections to GR, and really all we now care about are the sign. It's much easier to measure the sign of something than its actual value, right? You just need to know statistically, is it going to be positive or negative? And that's going to be enough to tell you something really powerful about the UV, whether you live in this column or not. Okay, great. So since we all come from very different communities, right, and we probably have very different ideas of what it means for quantum gravity theory to be causal or local or unitary, this slide is just to kind of summarize quite precisely what I mean. So say you take your favorite quantum gravity theory and you want to know, is it unitary, causal, and local according to Scott? So this is what you would have to check. Actually, I really mean four things. You'll see why in a moment. So thing number 0 is that, you know, for me, I really want to focus on UV theories of quantum gravity in which low energy scattering amplitudes can be extended somehow into the UV. Okay, so the idea is something like this, right? I'm defining some complex function of a single variable, p squared. And at low energies, I have my field theory. I know how to compute an amplitude in a field theory. I can compute some correlator and Fourier transform it. But at very high energies, I'm just assuming that this object is something. It's just something in your theory, right? The reason that I'm making this assumption, I'm just assuming that it exists. And that's important because now I'm going to define what unitarity, causality, and locality mean in terms of this something. So what causality means is that this something, right, whatever in your favorite theory kind of UV completes the amplitudes, that complex function should be analytic, an analytic function of S, right, in the upper half plane. And that might sound a bit cryptic, but really from a field theory point of view, what that means is that space-like measurements commute with each other. That's what it would mean at low energies. And what we're assuming is that in the high energy completion, you retain that quality, even if you no longer really know what it means to have space-like measurements. Right? You do have this complex function by assumption 0, and it is analytic by assumption 1. Assumption 2 is then unitarity, which is that this complex function has a positive imaginary part for any real value of S. And in the field theory, this is just the statement that the Hilbert space has positive norm. And again, we're just assuming that property is preserved when you go into the UV. And finally, locality is something about the very high energy limit when S goes to infinity. Right, this ratio of the amplitude divided by S squared should vanish. And that's really telling you that you can inverse Fourier transform from momentum space back to position space and talk about amplitudes in position space. Okay, good. Perfect. So for instance, string theory definitely ticks all these boxes, right? There is a well-defined object which would be the high energy completion of any scattering amplitude. And you can check that that object in string theory ticks these boxes. Now, one thing the organizers mentioned to us when describing the session was the possibility of setting some kind of challenge, right? So here you have in the audience people from all different communities working on very different approaches to quantum gravity. And so for me, what is the thing that I would like to know most from all of these different communities? I would like to know, to what extent can you tick some or all of these boxes? Okay, so I mentioned that some discrete approaches don't tick these boxes, and usually that's just because there isn't a meaningful thing that you can define in the UV that sort of UV completes this amplitude. But I'm quite sure that there are approaches beyond string theory in which there is some meaningful high energy limit of an amplitude, and I would be super interested to know, like, to what extent you tick these boxes. But for the rest of today's talk, right?
Excuse me.
Sorry, this is a minute warning.
Oh, thank you for the warning. Yes, excellent. Very good.
Could I ask a question?
Yes, please, go ahead. Yeah.
Could you elaborate on the locality condition and why you call it locality, and what more precisely what it means about what's local and in what sense?
Yeah, okay, that is a good question. So I actually have some backup slides at the end that say a bit more about each of these assumptions. So maybe I'll postpone your question until the end then, and do ask me it again if I forget to come back to it. But yeah, absolutely. So for now, you should think of this as some checkbox that in principle you could imagine taking your favorite quantum gravity theory, computing whatever UV completes this amplitude, and then checking whether this limit vanishes. And I just want to know the answer, yes or no. Okay. And if the answer is yes, then I would put your theory in this left-hand column. And if the answer is no, I would put it in this right-hand column. And then I'll come back at the end to maybe say some more words about, semantically what that means physically.
Okay, I have one other question real quick.
Yeah, sorry,
you mentioned earlier when you were listing possible UV completions, Horsjava gravity was one of them.
Yeah.
And that doesn't respect Lorentz invariance. But it seems like one of your conditions here, you're assuming somehow implies or relies on Lorentz invariance, the causality one.
Yeah.
So I'm just wondering, do you agree that whatever you're going to talk about, it would not apply to theories that violate Lorentz invariance?
Yeah, that's right. I would have put Horaver-Lifshitz in this column on the right-hand side. Yeah. Yeah, for the reason that you mentioned.
Thank you.
Good. Perfect. Okay.
Can I ask a quick question too?
Yes, I think so.
Just how would you include the presence of black hole in this formulation? Where does that fit in your axioms?
Presence of black holes. Given that maybe doesn't have a short answer, again, I'll postpone the discussion to the end. So for
Well,
sure,
in the sense
I
that
can compute
at
these.
high energy, you expect, certain modification.
Absolutely.
of
So at
these
high energies, you
amplitudes that
do
you're
expect
talking about.
black holes. That's right. So at low energies, I can compute these amplitudes. Okay, because at low energies, everything's perturbative, and I don't need to worry about collapse into black holes. Now, at high energies, I will generate black holes, and exactly what black holes do in the UV, that depends a little bit on your approach. So one of the approaches I mentioned on the previous slide was classicalization, this idea that if you scatter very high energy gravitons, you'll just create some black hole, and that will Hawking radiate lots of low energy photons, and you have this UV-IR mixing that takes your high energy states back to low energy states. Right, so that's an example of some UV approach in which the formation of black holes is very important and would require something quite tricky here in the something that defines something in the UV. But then there are other approaches where black holes play a different role. Right, so that's why I'm not saying anything specific about what black holes do, because that's going to be an approach dependent answer.
Can I make it also remark?
In the interest of time, let me remind everyone that we have like a half-hour saved for discussion at the end of both talks.
Okay.
So if you have very quick clarifying questions during the talk, that's great.
I wanted
I would
to,
ask to save discussion for later.
I hope it'll be quick. It is with regard to Ted's question. Okay, Ted's remark. In algebraic quantum field theory, the item 1 is what is called locality. There is no item 3. So there is no item 1 is what is called locality, but it requires a mass gap. Item 3 looks to me like Froissart bound. Maybe it is not. It looks like, but that doesn't really capture what is meant by locality. And I want to make one remark. There have been now a number of papers that at low energies, there is Lorentz invariance breakdown because of infrared effects. They are quite rigorous results coming from the latest one was by Mund, Reren, and Schroer. It's a long paper, and they have proved that Lorentz invariance is actually broken at low energies, and in fact, the standard notion of locality does not apply.
Okay.
And in fact,
maybe I can postpone some of this discussion until the end. So let me say that here I'm defining. When I say locality on the slides, what is it I'm referring to? I'm referring to this boundedness condition. So that's, if you like, that's just my definition for the purposes of this talk. And I completely agree that there can be other definitions of exactly what this means. Yeah, absolutely. And I'd be very happy to talk about those.
There is another problem, because it is emerging that there is no Lagrangian field theory description at all at low energies. Okay. So one cannot write an effective Lagrangian. Right,
great. So here, UV theories in which you can write this low energy description. Okay, they go on the left-hand column, ones in which you can't go on the right-hand column. Okay, there's some meaningful way to separate your quantum gravity theories into two columns. And so what we're going to use, right, in the final kind of couple of minutes I have, is we're going to use the following result, which is that if you have this UV theory, which is unitary, causal, and local, right, that satisfies the properties on the previous slide, then you can show that this low energy scattering amplitude is bounded in the following sense. When you take derivatives with respect to the total incoming energy, that has to be a positive number. So that gives you a way to carve your parameter space up into two boxes, right? And then check experimentally whether you think you could come from a UV completion like string theory or some other UV completion. Fantastic. So to show a kind of application of these bounds in action, I want to talk about dark energy. So a particular EFT that captures dark energy. And so let's get phenomenological. Okay, what is the EFT that I'm going to use to illustrate these bounds? I'm going to take the following 2 degrees of freedom. So I'm going to imagine that at very low energies, you have both the space-time metric and a light scalar field. So this light scalar field is going to play the role of dark energy. And as we know, light scalar fields, you can get an abundance of them in various quantum gravity models. Okay, so this is one of those light scalar fields. It's going to play a cosmologically relevant role. Now, the most general effective field theory that involves a light scalar field and the metric, there are lots of different interactions I could write down. So to make this problem tractable, I'm going to add some extra symmetries in addition to diffeomorphism invariance. I'm going to require that this light scalar has a Z2 symmetry, so I can flip its sign, and also something called a Galilean symmetry, which is really like a souped up shift symmetry. I can shift by a constant and also by any constant multiple of x. Now, the reason I assume these symmetries is that together with a derivative expansion, right, that all my derivatives are small, the effective field theory, the leading order effective field theory is actually very simple. Okay, it's something called the quartic-Horndeski Lagrangian. It has 3 terms. So let me just tell you what each of the 3 terms are. The first term is basically, it's like the Einstein-Hilbert term, only now instead of a constant Planck mass, I have this function g4 of x, where x is like the kinetic term for phi, it's d phi squared. And the second term is a bit like lambda. It's a bit like the cosmological constant, only now it's not a constant, it's some function g2 of x. And then there's a single interaction that I can write down involving second derivatives of phi, okay, at this order in derivatives. And the Galilean symmetry guarantees the special antisymmetric structure. Okay, very good. So the point is that with these inputs, okay, this is my EFT. What are the EFT coefficients? Well, it's these functions g2, g4, and their derivatives. So phenomenologically, how am I going to measure these things, right? What are the experimental constraints on g2 and g4 and their derivatives? Well, g2, right, because it's just playing the role of lambda, really that's the thing that fixes my background space-time expansion. Okay, so you can pick a g2 so that you get something that looks a lot like lambda CDM at the background level. Okay, so that's not something that I'm going to focus on today and not something I'm really going to constrain. Really where the action is in g4, right? So this function g4 really determines how the perturbations on top of this cosmology evolve. So perturbations in this model are going to evolve very differently to lambda CDM. So I can put experimental constraints, tight experimental bounds on g4 and its derivatives. Okay, so in particular, the g4 without any derivatives, that's just the effective Planck mass. Okay, it controls the strength of gravity on large scales. And the first derivative of g4, it's often something we call CT squared, and it's the speed of very low energy gravitational waves. And the second derivative of g4 is this alpha b parameter, controls how the scalar field self-interacts. So on very large scales, how does the dark energy lumps cluster together? Good. So that's the theory I'm going to constrain. This is the phenomenology, right? These are the things we can measure. And so the only missing part of the puzzle is what do these positivity bounds mean in this context, right? Suppose you had a unitary causal local UV theory. What are the allowed ranges for G2 and G4? Okay. So I'm going to give you a couple of examples, and then I'll stop and take questions. So get ready for the first example because it's a doozy. So the first process, right, that I want to derive a bound from is this scattering process here, where you have this light scalar phi and some matter field. It doesn't really matter what the matter field is. It could be a standard model field like the Higgs. But they come in and they interact and they go out again. They don't couple directly to one another, but they both couple to gravity. So there is some interaction mediated by metric fluctuations. And the answer is s squared times the first derivative of g4. So these positivity bounds, right? The fact that the second s derivative has to be positive thing, that's really telling me that CT has to be bigger than 1, right? That gravitational waves have to be superluminal, right? In these units, 1 is the speed of light, and CT is the speed of low energy gravitational waves. So this is not a typo, and it's something that took us a bit of time to kind of wrap our heads around, right? This is super striking. The claim on this slide is literally that if you have these properties, right, causality, unitarity, and locality, as defined earlier in the UV, right, for instance, string theory, then at low energies, you're going to land on an EFT in which very large wavelength gravitational waves appear to be superluminal. And so the way that we eventually, got ourselves to sleep at night, right, after learning this, is to realize the following. So we bang on and on and on about how, light is the fastest thing and nothing can go faster than light. That's what we teach kids in high school. But actually, maybe that's not quite true, right? Probably it's the speed of gravity which should be the fastest thing, right? That makes sense from the point of view of causality. Causality is all about what light cones do. You really want gravity and gravitational waves to be the fastest thing. And so this condition that CT is bigger than 1 here is like the speed of massless matter, the speed of photons, the speed of any other massless thing like the Higgs. So this is just saying that matter fields go slower than gravitational waves. And when you put it like that, it all kind of starts to make some sense. Good. So if the organizers will let me, I'll give just one more example, and then we'll call it a day. So the second example is you actually get more bounds on this theory. So if you consider scattering not phi and matter, let's say you scatter phi with phi. So in this theory, there's some contact interaction. And then because phi couples to gravity, there's also this gravitational interaction. And so now the scattering amplitude has two terms. But again, these axioms, right, in the UV, unitarity, causality, and locality, they tell you that this coefficient has to be positive. So that gives you now a bound that mixes these two phenomenological parameters, right? There's a bound that says that this alpha b, right, how dark energy clusters on large scales, that has to be less than this function of the gravitational wave speed. Okay, so now you can make these awesome plots, right? You can make plots like this, where here on the y-axis, it's literally the speed of low energy gravitational waves. On the x-axis, it's this braiding parameter. So it's how strongly do dark energy fluctuations cluster on large scales. And the orange contours are showing our best observational constraints from large scale cosmology, from the CMB and baryon acoustic oscillations and the matter power spectrum. Great. Cool. So that's your experimental data, right? But this theoretical bound that we've derived from these considerations of unitarity, causality, locality in the UV, and they actually cut your parameter space into two regions, right? There's this green region, which is really defined to be the region that satisfies this bound and also has superluminal gravitational waves. So it's kind of like flat here because you're demanding gravitational waves are superluminal, and then this curvy bit is from this bound. Okay, and that is the only place that string theory could ever land, right? Whereas if you had any of these other approaches that violate one or more of these assumptions, then you can land anywhere. So this is really cool for two reasons, right? First reason is, as you might expect, that the data sort of points in the wrong direction, right? The data seems to want to pull you to this lower right-hand quadrant, but these positivity constraints push you to the upper left. Okay. Having said that, right, you should really interpret this, I think, as a kind of proof of principle, right? These contours are like 1 and 2 sigma. And this point here, the crosshairs show you GR, like 0, 0. So really the data is not statistically significantly discrepant with GR, and GR is allowed in this positivity, island. So I wouldn't say this is a discovery that string theory cannot describe our universe. But what it does show is that with next generation surveys, right, we expect these contours to shrink by a factor of 5, 10, something like that order of magnitude. So these contours are going to get a lot smaller, right? And if they stay in this region of parameter space, we're going to then ask very serious questions about whether the UV could tick these boxes and be consistent with what we see in large scale cosmology. And the other reason why this, identifying this green region is really important, right? This kind of harkens back to what I said at the beginning. These parameters are, quite hard to measure. This is quite a large, blob of experimentally allowed values. And so what you can do is you can play this game the other way. You can say, okay, I am just married to the idea that quantum gravity has to tick these boxes. It has to be unitary, causal, and local, or it has to be some kind of string theory, for instance, right? So I don't believe really that I should be fitting the data with any value that is not in the green region. Okay, so you can redo the fits, right? You can talk to a Bayesian statistician. You can ask them to redo the fits with the prior that you have to live in this green island. And the resulting experimental constraints are now this black blob here. Okay, so rather than looking at a 2D plot, it's cool to look at a 1D plot. So this is if you marginalize over the gravitational wave speed. You see that the orange curve is like data alone. And then the black curve is like data plus these positivity priors. The red curve is if you just put one prior and not both. So, but what I want you to compare is like the orange one and the black one, right? So what's happening is the widths of these Gaussian distributions are getting a lot smaller. You basically have a much better handle on what you think this braiding parameter is, right? Because you've put in extra information about the UV. Fantastic. Okay, very good. So I've gone a little bit over time, so I apologize for that, but there were a few very good questions. And so if I don't really have time to address them now, I think after the second talk, there will be a dedicated discussion session. So I hope we can come back to some of those points then. But just to sum up, right, the first point I wanted to make is that this effective field theory language is really a way to compare very different quantum gravity approaches, right? Any quantum gravity approach, no matter how different at high energies, at low energies is just a list of C0, C1, C2 of Eft coefficients. So you can really compare like how close two different quantum gravity theories are by just looking at how close these two lists of numbers are, right? The second thing was that in particle physics, we often play this game of identifying some UV feature, which would lead to a bound on the Eft coefficients. And then if we ever find that that bound is violated, we can then forbid whole classes of UV completion. So that was the game that I then tried to play for the rest of the talk, right? In quantum gravity, if we have these kind of three assumptions, unitarity, causality, locality postulates in the UV, right, that would mean that in the IR, these amplitudes are bounded. And so then you can go away, take your Eft and compare that region of parameter space with what data tells you. And in the context of that particular dark energy Eft, it was super striking, right? It told you gravitational waves had to be superluminal, which in retrospect kind of makes sense. But it also told you this interesting relation between how dark energy clusters and the gravitational wave speed, right? Which can really help trying to determine these low energy parameters. Fantastic. So thank you all very much. That was everything I wanted to tell you today.
Okay, thank you so much, Scott. I'll applaud for everyone for a very interesting talk. In light of time, I think it is best if we go straight to Irene. But of course, I'll mention again, as you did, that we have a dedicated half-hour of discussion afterwards. So any of these interesting discussions that sort of were initiated during the talk, we can save for later. Okay, so Irene, if you want to share your screen. Perfect. Okay, great. So Irene, can you hear me, by the way? Or, okay, good, and we can hear you. So for our second talk, we're very happy to have Irene Valenzuela visiting us, I guess now from Spain, but currently at Harvard, who will be telling us about the Swampland program, the quantum gravity imprint at low energies. Take it away, Irene.
Okay, thank you very much. Thank you for the introduction. Thank you, Scott, for the talk, and thank you, the organizers, for the invitation, and also for organizing this virtual series of seminars. I was taking a look. I think it's a great idea. I think it's written in the website. There are many different approaches, and I think we missed to have events of this type in which we can join and discuss about quantum gravity, which is what we are all interested in. So thank you for doing this, and thank you for the invitation. Okay, so yeah, my plan is to give you some brief review about what the Swampland is about and what are the most important ideas and why we are so excited about it. I mean, what are the possible implications? So let me also start very basic. As Scott was saying, we are used to work with effective field theories. This has proven to be very useful. In the past, we formulate some effective field theory description that is valid up to some energy scale and describes the physics at that energy scale or below. And we always know how, if we have an effective field theory description, how we can integrate out the fields to have the description in the IR, as Scott was doing. But sometimes this approach of effective field theory can make you think that you can also do the process the other way around. So that given an effective field theory, you can always complete it in the UV with another effective field theory. And the point is that that's not always true. Okay. So the question that we are trying to answer is, what are the constraints or the rules that a given effective field theory has to satisfy in order to admit a UV completion? Okay. So already in quantum field theory, this is not always possible. We cannot always UV complete the theory. But in quantum gravity, this is even more important because we see quantum gravity is more constraining. And the point is that we need to satisfy additional constraints beyond anomaly cancellation. So this is the typical thing. I mean, we typically require that theory is anomaly free and so on. But there are more things that we need to satisfy in order to allow for a UV completion of our favorite effective field theory in a consistent quantum gravity theory. So the word Swampland refers to those effective field theories that seem apparently consistent from an IR perspective. Maybe they are anomaly free, maybe they look unitary and so on, but still they cannot be UV complete in quantum gravity. And the name appeared in opposition to the landscape, which is the name that we were using in string theory to describe those low energy descriptions that can arise. Okay, so the goal of the Swampland program is try to make this precise. So try to understand precisely what are these constraints that quantum gravity imposes at low energy. So what distinguishes the landscape from the Swampland? And this is, of course, a very ambitious goal because we don't have a complete understanding of quantum gravity yet. But I think it's very important because if we understand these constraints, I mean, this is like the UV imprint of quantum gravity at low energies, and they can have important phenomenological implications. Okay, so new constraints mean new guiding principles to construct beyond standard models of particle physics and cosmology. And also, they can bring new insights to solve the naturalness issues that we observe in our universe. How is that? Well, because what we see by working on the Swampland program is that sometimes these constraints are very surprising from an EFT perspective. Okay, so the typical things that we expect or that we call natural from EFT maybe are not natural at all in quantum gravity. And this, as I put here, one of the take-home messages that one should take is that these EFT expectations that we have can fail in the presence of gravity. And this is great news because if they fail, then we have something new to tell to someone working on the IR. Okay. Okay, so what are these constraints? Well, okay, this is the hard question, of course, and we have some proposals of what these constraints can be. They are called Swampland conjectures, and typically they are motivated by string theory or by thinking of black hole physics and so on. Now, even if these ideas are born, some of these ideas are born in string theory, they are supposed to be valid beyond string theory. Okay, so what we are trying to do is to use string theory as a framework, as a toolbox to derive what properties are really fundamental in the sense that are required by consistency of quantum gravity, and to distinguish that from those that are purely technical things of the different compactifications. So the goal is try to extract the general features, okay? And of course, I mean, then in order to make sure that it's a general thing, we need to gather more evidence for them beyond string theory. So that's why we need to attack these conjectures from different perspectives. The more perspectives and the more research areas that get into this, the better, because then it's only when we gather evidence from different viewpoints that we get more and more confident that these conjectures hold in general in quantum gravity. Okay. So at the moment, the different approaches that are taken in the Swampland program are string theory, working in string theory. Black hole physics is very important, like thinking of black holes as also a lab for quantum gravity. Holography, ADCFT, and also all this causality, unitarity, and positivity constraints that Scott was talking about. Okay, so working on the Swampland program is more like a mixture of different people with different backgrounds that are using their own expertise to try to answer the same type of questions. Okay, okay, so these are the different, the most important Swampland conjectures that we have right now. What I want to remark especially is that one of the things that we are discovering is that these conjectures, even if originally most of them were formulated independently, we are discovering more and more relations among the conjectures, which suggest that they might be just different phases of the same underlying principles that we are starting to discover. So one of the goals of the Swampland program is also to study these connections, to try to reduce these conjectures to the minimum number of principles that would reproduce everything. And with the years, we are reducing and connecting more and more these conjectures. Okay, so the plan for the rest of the talk is to explain a little bit this map. Okay, So there's some order here, like not all the conjectures are the same. Like, for example, in the top row, the conjectures are more about the kinematics of the theory. Then in the middle row is about constraining the spectra. And at the bottom, we have constraints on the scalar potential and interactions. So in the same way that they are about different parts, they also have a different level of evidence. Okay, so it depends a lot what conjecture we are talking about. We have evidence only coming from string theory, or maybe also from black holes or other things, or positivity bounds and so on. So it really depends which one. Not all of them are at the same level. Okay, and this is important when considering also the phenomenological implications. So I'm going to describe a bit, like briefly, what they are about and the phenomenological implications, focusing mainly on these three that I put on purple, because these three conjectures are really the center, the core of the Swampland program. Okay. Okay. So yeah, one of the most important Swampland principles, and one of the oldest one as well, is the absence of global symmetries in quantum gravity. Okay, so it's the statement that global symmetries cannot be exact. They must be broken at some energy scale, or they are not global in the sense that they are gauge. They are associated to some gauge degree of freedom. Okay, so in order to explain this, it's very important to take into account, I mean, what is this definition of global versus gauge? Okay, and here I put just some intuition. Okay, so this can be formulated much more precisely, but the intuition is that gauged symmetries are associated to charges that you can measure from far away, while global symmetries, there is no way to measure this from very far away. Okay, roughly speaking. So these ones that you cannot measure from far away are the ones that we say are in the Swampland, in the sense that they are not consistent with quantum gravity. And just to give you an example that we are all familiar with, if you take the standard model, you have the decay of the neutron. This process have two conserved charges. One is global, that is associated to B minus L, so baryon minus lepton number, while the other one, the electric charge, is gauged, okay, because it has some electric field associated to it. So thanks to the electric field, we can measure the electric charge from far away, but we cannot measure this B minus L. Okay. Okay, so why is it a problem that, I mean, why global symmetry should not be allowed in quantum gravity? Why is it a problem that we cannot measure something from far away? Well, there is already a way to understand what the problem could be just by thinking of black holes. Okay, if you consider some black hole and you throw particles with different charges, different global charges, so that you can generate different black holes with different values of the global charge. This global charge is, I mean, the black hole is the near horizon and everything is insensitive. Doesn't distinguish this global charge. We cannot measure from very far away what this global charge was. This black hole will only be determined in terms of the mass and the gauge charge, if it has any, or the angular momentum. So by constructing black holes with different global charges, we end up with having an infinite number of ways to generate the same type of black hole. And this infinite number of ways translates, roughly speaking, into an infinite entropy, okay? Because the entropy of a black hole intuitively is like a measure of how many different ways, how many microstates I have to create the same object, the same black hole. So this is just a heuristic argument. You can also explain it in terms of trouble with remnants, in the sense that you can let these black holes to evaporate. They will reach almost the same mass, but still they will be different. So you have infinitely many stable things that will ruin any Eft weakly coupled to gravity. Okay, so that's why it's very important you can distinguish it from far away. Now, this is the heuristic argument that is based on black holes and that make us think that it's something general of quantum gravity. But of course, the reason why this is one of the most important conjectures is because we have rigorous proofs in different contexts. Like we know that there are no global symmetries in perturbative string theory, There are also more recent proofs in holography, in ADS-CFT, because of locality of the CFT. And recently, it has also been correlated to the unitary black hole evaporation, so in a more rigorous way, not just these heuristic arguments. So all these developments, if you have heard of about deriving the page curve, using replica wormholes and so on, are also useful to show that global symmetries are broken in this process. And more generally, if you have a topology changing process, so some process that changes the topology will also break this global symmetry. So in order, I mean, the intuition that I have why these global symmetries are not allowed in quantum gravity is because quantum gravity topology itself fluctuates. It's not only that the geometry is not fundamental, we know this by Einstein gravity, but also the topology can change, and all these processes are breaking these global symmetries that typically are described by a topological operator. Okay. Okay. Anyway, so this is the conjecture, which today, I mean, in the context of string theory and holography, is more a principle than a conjecture. And now you can wonder, okay, what are the possible phenomenological implications? Now, I was discussing the case of B minus L, but it's true that all we can say is that either it's broken at some high energy scale, okay, which would lead to proton decay and so on, or it's gauge, in the sense that there is a new fifth force associated to it. Now, in order to have really an important phenomenological consequence, we should be able to quantify at what scale is broken, how much is broken, and how weakly coupled is this new gauge field. And in this sense, this conjecture by itself is not very constraining because it's just telling you that they cannot be exact, but it doesn't tell you how much they have to be broken. Okay, so the weak gravity conjecture that I will explain next can make this statement stronger because it precisely quantifies like how much we have to break this symmetry or how weakly coupled this gauge field can be. Okay. Now, before talking about the weak gravity, I just want to mention one thing that in the past year or the past 2 years, we are starting to realize that even without the weak gravity conjecture, just thinking of global symmetries, we can extract some consequences that suggest that this conjecture is more constraining than what we originally expect. And this is thanks to all these new generalized notions of symmetries that are arising in the QFT community, because this leads to a new zoo of global symmetries to explore, much more general than this ordinary symmetry that we were discussing, like B minus L. And all these P4 non-invertible global symmetries and so on, they have really an impact on the dynamics of the theory. And there are several things that you can derive. For example, recently we saw that completeness of the charge spectrum seems to follow from the absence of global symmetries. If we generalize this notion of global symmetries to non-invertible ones, this allows to give some relation between different Swampland conjectures that were formulated. So this completeness hypothesis, so the fact that you should have states with all possible charges that are consistent with Dirac quantization, was an independent conjecture, but now we can see that follows just from the absence of global symmetry. So it goes in the direction of unifying conjectures, okay? And also, if we think of more general symmetries associated to topological global charges, and we combine these with supersymmetry and anomaly cancellation, people have shown that this is enough to rule out some supergravity theories by constraining the rank of the gauge group. So you can constrain what possible theories are consistent with quantum gravity just by requiring the absence of global symmetries. You have some supersymmetry. And this is some area of research that is gathering a lot of attention in the past year. At the moment, people have been able to show that for dimension bigger than 6, okay, this is right now a lot of high dimension and supersymmetry, so it's a bit far from, it's very far from our world, but it's like a proof of principle of how this can be more constrained than we expect. People are showing that all supergravities in dimension bigger than 6 that satisfy this principle, so the absence of global symmetries and anomaly cancellation, indeed they can arise from string theory. So people are trying to invert the question and try to answer or try to find out whether everything that should be consistent with quantum gravity can arise from string theory or not. Okay, and this is what is called string universality, whether everything somehow will be connected to string theory in one way or another or not. So how much we are under the lamppost if we only look at string theory. So this is an interesting area of research, but let's try to move on and go to something more similar to our world right now. Okay, so this is for the case of no global symmetries. Now I want to say a few words about the weak gravity and the distance conjecture, okay, which constrain the field spectra of the theory and quantify how much we have to break these symmetries in a way or another. Okay, so these conjectures, broadly speaking, predict the existence of new light states, okay, whenever the effective field theory contains some weakly coupled theory or some large field range, in the sense that there is some scalar field that takes a large, very large vacuum expectation value. Okay. So here I have the definitions of the two theory, although because of lack of time, there's no time to enter into the details. Let me just say that the case of the weak gravity constrains the spectra in a gauge theory. So if you have some gauge field, you need to have some particle, some state with a mass that is smaller than the charge. Okay, so it constrains the charge to mass ratio of the particle in terms of the extremal, the value of the extremal black holes. And the distance conjecture constrains also the mass of the states, but in terms of the vacuum expectation value of this scalar field. So it's, rather than the charge. Okay, so it tells you that if the vacuum expectation value of these fields is very large, you are going to get new particles, new states that become light because they behave exponentially in terms of this vacuum expectation value. Okay, so what I want to do now is just, rather than enter into the details, what I want to do is to extract the general feature of these two conjectures, which is that the fact that the Eft can break down at a scale that is much below the Planck scale because of quantum gravity effects that are associated to a presence of an infinite tower of states that is becoming light. Okay, and this happens whenever we have a small gauge coupling or a large field range. Okay, so the weak gravity conjecture, since the mass has to be smaller than the charge and the charge depends on the gauge coupling, tells you that you need to have light states when the gauge coupling is small. And the distance conjecture is similar. When the large field, the scalar field takes a very large vacuum expectation value, then you have new states that become light. Okay, so this is an example of something which is, actually, let me say this. So it's surprising from an Eft viewpoint, because why do I need to get new states when a gauge coupling is small or a scalar field is large? I mean, that's completely fine in quantum field theory. You can have a gauge theory which is weakly coupled and there is no problem at all. But quantum gravity is telling us that something has to go wrong. Okay, something must happen. There are an infinite tower of states that is becoming light if you try to engineer that. And the Eft is going to break down. Okay, and it's going to break down at this cutoff, which is much below the Planck scale. Okay, so even if the Planck scale is very high in energies, quantum gravity can have an effect at low energies. Okay, the cutoff can be much lower. And this is surprising from an Eft viewpoint, but it's very natural from a string theory perspective, or also very natural if we think of global symmetries, because when we try to make a gauge coupling very small, we are going to restore a global symmetry, okay, because we engage that symmetry. So if global symmetries are not allowed in quantum gravity, something has to happen that forbids you to take this gauge coupling too small. Okay. Okay.
Oh, sorry, Irene. This
Yes.
is a 4-minute warning.
Okay, fine. So this is the main feature, okay, of these conjectures that I want to remember. And let me just mention that, okay, what I want to do now is just to very briefly show a list of the evidence that we have for this, so you understand like where it is coming from. and then some brief comment about the phenomenological implications. Okay, and then I will finish with one example of these phenomenological implications, and that's it. So I hope to finish in 5 minutes. Okay, so the evidence, let me just go quickly. I mean, of course, we have a lot of evidence coming from string theory that has led to very interesting connections actually with mathematics. So some of these Swampland conjectures can be related to conjectures in mathematics and can be proven in that way using the geometry. Also in holography, there are different works about translating these conjectures to properties of the conformal field theory. Black hole arguments are very powerful for this, like to show that you need to have these states in order to avoid well, like remnants and to violate entropy bounds and so on. And there are also nice relations with weak cosmic censorship. And finally, there are also some relations using positivity and unitarity bounds, although at the moment, these unitarity bounds and so on are only able to reproduce mild versions of these conjectures, okay? And not the fact that you get not only one state, but infinite number of them becoming light. Okay. So just quickly, basically, what are the possible implications? So the weak gravity conjecture is going to constrain EFTs with tiny gauge couplings, okay? Or equivalently large axionic decay constants, because a decay constant is like the inverse of the gauge coupling for an axion. And the distance conjecture is going to constrain effective field theories with large field ranges, like happens in inflation, in which a scalar field rolls down a potential for a large field variation. Now, I just have here a plot to show that, of course, we can translate this to an upper bound on the maximum field range that can be accommodated by an effective field theory in terms of what is the cutoff of the theory. And if we want to require that the Hubble scale is smaller than this cutoff, this gives a bound in terms of the tensor to scalar ratio in inflation. Okay, so it's just an example. And just to be clear, the conclusion is that large field inflation is not ruled out, but is constrained. So there are models that are allowed, but there are others that are constrained and wouldn't be allowed by these conjectures, and therefore in quantum gravity. Okay. So if I have, I think 2 minutes or 3 minutes maximum, I finish the talk. So let me, yeah, so we have seen the first 2 rows of this map. And now I just want to finish with one example of which is more, I think, it's one of the examples that I find more interesting or exciting for phenomenology. But it comes from assuming these conjectures on the bottom. Okay, so these conjectures in the bottom are less understood. Okay, they are typically derived as consequences or generalizations of the weak gravity or the distance conjecture. Like you try to understand, okay, what is the effect of this tower on the scalar potential or the interactions and so on. But apart from this connection to the other conjectures, the evidence comes purely from string theory at the moment. Okay, so this is something that we need to understand better. Like the other conjectures have also arguments coming from black holes and other things, but these ones in the bottom, so far the evidence only comes from string theory, and it's still not clear. I mean, we are still work in progress to understand exactly what is the precise formulation of these conjectures and how general they are. Okay, but just so you have an idea, I mean, just what they are about. So we have the statement that a non-supersymmetric vacuum should be metastable. So the only way to guarantee complete stability is supersymmetry. Also, that when we have a large field variation of the scalar fields, then not only we have this infinite number of states becoming light, but also the scalar potential presents a runaway. So that implies that you cannot have a de Sitter vacuum, for example, okay, in these regions. And finally, there is this ADS distance conjecture that tells you that if you have a family of vacua with different values of the cosmological constant, and you approach the nearly flat, the flat space limit, you approach Minkowski, because this cosmological constant becomes very small. This would also come together with an infinite number of states that scales with the cosmological constant. So for the case of ADS, this favors scale separation, and it's a very interesting question to try to prove this in the CFT. Anyway, so if you take, I mean, just to finish, if you take these conjectures, you can get some interesting implication for the standard model of particle physics that I will show you right now and finish the talk with that. So the message is that quantum gravity, as I'm showing you, does not only constrain non-renormalizable, like irrelevant couplings, okay? So it's not only about the higher derivative terms, as we derive from the positivity bounds and so on. It's much more constraining. All these conjectures I'm talking about, they constrain also the spectra of the theory, the masses, the charges, the scalar potential, the possible vacua, okay? And they can really have an impact on the EFT. So they are really inducing some UV-IR mixing, okay? So this notion that we have of the separation of scales that comes from a Wilsonian effective field theory approach breaks down in the presence of gravity, okay? It's something that we already see with black holes, okay, that they mix the UV and IR, but also happens in string theory, and I think it's a general feature of quantum gravity. And I find it very exciting because this UV-IR mixing can also be the missing piece that we observe behind these naturalness issues in our universe. So the example that I promise you is that if you take the standard model of particle physics plus gravity and compactify on a circle of radius r, you can study what is the vacua that you get in lower dimensions, okay, just as an exercise. And you have a contribution from the cosmological constant, and then you have a piece which is the quantum corrections, the Casimir energy coming from all the particles of the standard model. And since our cosmological constant is very small, these quantum corrections become very important. Okay, so the spectra of the standard model really matters to determine what are the vacua that we get in lower dimensions. And the game now is that if the standard model is consistent with quantum gravity, their compactification should also be consistent with quantum gravity, okay, by background independence of quantum gravity. And what we can do is to use this to determine what are the constraints on the field spectra that a beyond the standard model proposal has to satisfy to avoid that this scalar potential in lower dimensions develops a minimum that would go against these Swampland conjectures. Okay, so just to show you the result, if you do this, it's very easy to show that this is the potential that we will get in 3 dimensions from the standard model. If we have, since we have more, let me say, we have bosons that are massless, but we don't have fermions that are massless. It means that the potential, even if it starts positive because of the cosmological constant, is going to go down because the bosons have a negative contribution. And the only way to avoid an ADS vacuum is that we have light fermions that are light enough to avoid the potential to go to negative values. And this light enough means that the mass of the fermion has to be smaller or the order of the cosmological constant. Okay, so in order to avoid this ADS vacuum, which would go against these ADS Swampland conjectures that I explained before, we need to have a surplus, like we need to have light fermions in our theory, and like a net number of fermions whose mass is of order cosmological constant or lower. So what are these fermions? Well, one option is that indeed they are the neutrinos. So this is a way to explain why neutrinos are so light in our universe. And this is a numerical coincidence that we observe in our universe, no? That the neutrinos are of order the cosmological constant or smaller, and can indeed have a quantum gravity origin. Okay, so you can translate this, in fact, to an upper bound on the electroweak scale, no? By writing the neutrino mass in terms of the Higgs wave. And this is relating both naturalness issues. Okay, so you could say, okay, if you have a universe with a cosmological constant that is small, then the electroweak scale also has to be small, because otherwise it wouldn't be consistent with quantum gravity. And this goes against the typical logic of naturalness and fine-tuning and so on. Okay, so these fine-tunings, I mean, are not real. It's just that not all the space of parameters are consistent with quantum gravity. So first you need to determine what is the space of parameters that is consistent, and then compare to the experiment. Okay, so this is it. This was just an example. Of course, there are many more phenomenological implications that one can derive from the different conjectures. So, of course, if you are interested in more details, you can ask me later or look at my review or different talks. Let me just conclude by saying that the message is that consistency with quantum gravity can have important phenomenological implications because not every EFT is allowed. And this is really constraining also the renormalizable part of the EFT. And we have proposals of what these constraints are. And we have more and more relations among them. So maybe they are just different phases. And in the future, we will just unify all of them into a few principles. But something that I find very important, I want to remark, especially in this series, is that it's very important to gather evidence from different research areas. And in this sense, we have improved a lot, but there is still much more work to do. And it would be amazing to make people working in other quantum gravity approaches to get interested about the Swampland program, to check if they are realized in their favorite quantum gravity completion or not, and what's going on. And that can help to formulate better these conjectures, or maybe to find one that is more specific to string theory than to others. But like the goal is to try to find what are the general principles that quantum gravity imposes at low energies. And for that, I think we need help from everyone. So thank you very much for your attention.
Thank you very much. Let's thank Irene virtually. Okay, so now let's open up to the discussion session. So either raise your hands or type your questions in the chat. The moderators and I will, or the organizer and I will forward them to the speakers. So yeah, if you have any questions, either Scott or Irene. I see Steve Carlip already has a question, so go ahead, Steve.
Okay, this is, I think, a fairly simple question for Scott. In your conclusion about the speed of gravitational waves, you must have somewhere in your analysis already have had the speed of light. Where was it? And shouldn't that have been the speed of gravity instead to begin with, if the speed of gravity is what's fundamental?
Okay, yeah, that's a good question. So the idea here is that the speed of gravitational waves runs with energy. So when I said the speed of very low energy gravitational waves, this is on this expanding cosmological background in which Lorentz invariance is spontaneously broken because the background is time dependent. So if you imagine very high energies, gravitational waves would have a speed 1 in these units. So what is 1 in these units? It's like the speed of the light cone that is preserved by your high energy Lorentz group. And then at low energies, your expanding space-time background spontaneously breaks this symmetry. So now your gravitational waves can travel at a different speed to 1. And so what this is showing is that speed always goes up rather than down. Thanks.
I see Laurent has a question. Laurent, go ahead.
Hi, Scott and Irene, thank you for your talk. It's more a question for Scott, but also for Irene. It's a very general question. You seem in your presentation to kind of I think you even said it, to assume that effective field theory is kind of a universal setting that you can, in which you can analyze quantum gravity. But from people that works in quantum gravity, there's another option that one of the fundamental assumptions of effective field theory, that there is a decoupling between the UV and the IR, is not there. And in your analysis, you are not presenting that other option. That is, you are not presenting the option that maybe effective field theory is not the language in which we should analyze quantum gravity. And if you think about it, that would be a very amazing possibility, because in some sense it will give us a wealth of new observables. So I think Irene commented on that picture. So somehow there's a tension between the two. And so the question is, okay, can we step back and have a framework that analyzes that effective theory is that we need to use, and then what should we develop instead? Because this absence of infrared UV decoupling.
Yeah, I mean, if I may reply, I agree. I think the effective field theory is a framework which has been very useful, but is very linked to a quantum field theory description. And quantum gravity is not a quantum field theory. And I think it can break with some of the expectations that we derive from EFT. Of course, in the end, at low energies, you should recover an EFT, but there might be correlations between the EFT parameters or things like that you wouldn't expect at all in EFT. So it's not maybe there's a better framework to have. I think, I don't know, I mean, of course, it's a big question. We don't know what is the framework for that, but I think it's very important to stop thinking of this separation of scales that is completely tied to quantum field theory and be open to the possibility that indeed quantum gravity induces a mixing between the UV and the IR. And this mixing can be, like behind some of the things that we observe in our universe. So this Wilsonian effective field theory approach might be the moment to modify it and get something new. And that's very exciting, I agree, because it's like a new way of thinking for the future, right? Like a new way to approach to progress in high energy physics.
Yeah, I mean, I would also agree. I think at a very crude level, we expect there is a range of scales over which your theory of quantum gravity should look like GR plus something small. But then you're right that the way we parameterize the something small, I mean, the EFT logic tells you to use a certain set of operators, but maybe that is not a good way to try and capture the small corrections in your theory. So I agree with what Rini said. I think that's potentially a very interesting thing to think about, other possible parameterizations that are not the ones that come from a kind of naive QFT reading of the situation. Yeah, absolutely. And I guess to tie in with some of the things that I was saying, I didn't really mention this possibility, but yeah, one way I would think about it is let's assume that this EFT parameterization is a good one. What would some of the observable consequences be? So for instance, some of these parameters would have to be positive, and then you can check, right? Then if these parameters are not positive, it could be evidence that this EFT parameterization is not a good one. Which I think would kind of tie into this idea that we should be looking more broadly at other kinds of parameterizations of these corrections.
Okay, I think Steve Giddings was next, so go ahead, Steve.
Yeah, thanks for nice talks, both of you. This is for Scott, a comment, and I think it starts to maybe address the questions that both Laurent and Ted raised. So you define locality in terms of basically the boundedness as S goes to infinity. In fact, in gravity, that bound is violated in certain regions of complex S. You can see that directly in terms of the iconal amplitudes, which are an approximation, basically at long distance. But then also when you include the likely effects of black holes on amplitudes, there are also arguments that basically polynomial behavior is violated, again, in certain regions of complex S. So, that's something you might want to include in the analysis, because you don't have necessarily polynomial boundedness. There is polynomial boundedness in the upper S plane, upper S plane, upper complex S plane. That's associated just with causality. By the way, but locality, I think, allows more general growth in other directions.
Right. Yeah, absolutely. I think, those are really good, really important comments. So about the possible UV behavior of the amplitude, right? One thing which I didn't mention in the talk, but recently there's been a lot of interest in assuming certain kinds of Reggie behavior at high energies for the amplitude. And then you can run the same sort of machinery and treat the Reggie behavior as some input. So there's some particular slope associated with the high energy growth, and then you can see what do your low energy measurements tell you about that slope. So rather than assume Frossard boundedness, like I sort of did in the talk, you can try and let that float as some free parameter that you don't in advance know. And then see if you can put bounds on it in some way, which I think is kind of maybe related to some of your comments there.
Yeah, I think you have to be careful about using, well, if you by Froissart boundedness, you mean sort of boundedness in the cross section. The Froissart bound is not something you normally prove in a theory without a gap. Right. Gravity obviously has massless excitation. So, but again, these comments about polynomial boundedness and so on of amplitudes in the complex S plane are more general, it turns out. So, but again, you can directly see the behavior. You can study very high energy scattering at basically large impact parameter, which is a regime which we think we understand. It's a lot like scattering of the Earth and the moon basically is governed by the iconal approximation. And those iconal amplitudes already start to exhibit some of the relevant behavior, which includes this non-polynomial behavior.
Ilam, you have a question?
Yeah, Bal is my name. Okay. Just a couple of comments, which I was trying to raise when Ted was speaking. Okay. The first is that there are a bunch of actually theorems, if you like, which are coming out already in QED and also in quantum gravity, that, for example, the electron does not have a sharp mass. An isolated electron does not exist. It's surrounded by the infrared cloud. So the mass spectrum is smeared out. So the entire analysis using standard locality principles and writing quantum fields and effective Lagrangians especially fail. These are theorems which are coming from the quantum field theory groups from Hamburg and Rome and so on. Okay? And in fact, the entropy which are caused by this mix, this smearing, has been analyzed by Longo. And I believe that in many cases this is infinite. So it seems to me that there are a bunch of results which are coming out that the entire effective Lagrangian approach cannot work when in the presence of massless particles. That's statement one. I believe this is correct. Second thing is you wrote phi. Is it a massless field? You wrote phi in your calculations. You wrote phi, and I didn't see any mass parameter.
Yeah, question directed to me. Yeah, yes. The idea is that phi is light because it has a shift.
It's a massless field. It's a mass, but the massless field does not exist in a spatially non-compact region. It is not a well-defined quantum field at all. The derivative of the field can exist, but not phi. Phi cannot. So I do not understand also your use of phi in the context of some effective Lagrangian. It does not. The first is, where is this Lagrangian? Lagrangian is a classical theory. So in the quantum configuration, it may not exist. And I am telling that there are theorems that are coming out that they don't exist, in fact, okay? Because the beginner analysis itself fails. So I don't know exactly how these issues are handled. One final remark, and then I will stop. There is a local observations. I think it was Steve Giddings. In quantum field theory, normally one talks about local observables. So you smear the field with local operators and look at the algebra of observables and look at the state on it. There's a theorems, if you like, that in standard quantum field theory, we expect these algebras to be of what they call von Neumann type 3-1. It has very strong properties, and in particular, every state can be approximated arbitrarily well by every other state up to unitary transformations. This is a theorem attributed to Kohn and Stromer. The result is that local, what is meant by observations, itself gets very confusing, not very clear. So I don't quite understand, and this is nothing to do with the energy scale, it's a mass theorem. So the fact that you have a type 3-1 algebra and the operate means the Kohn-Stromer theorem says that one cannot, Kohn-Stromer say that one cannot determine a state by measurements. You need some external thing to do the calculation. So I have a feeling that this effective Lagrangian approaches miss foundational problems of quantum field theory and of quantum gravity. Then I stop. I think I made enough negative comments. Nobody is commenting, but you can at least tell me about phi. Is it a massless field?
I mean, I think it cannot be a massless field because there is no global symmetry that could protect the field to be massless.
But
right?
massless field
I agree. Quantum gravity, I mean, you cannot have a massless field. So somehow in his Lagrangian, I guess you should have more terms so that it's not massless. And I don't know how then they compare to the higher derivative terms, but that's
right.
knows.
Yeah, no, you're quite right. All of these continuous symmetries, both the shift symmetry and the Galilean symmetry, they're softly broken by gravitational corrections. In fact, even without going to quantum gravity, you can see that the Galilean symmetry gets broken by graviton loops, and that's something you can compute perturbatively. So you're right that there's small corrections are radiatively generated by the fact that you're trying to couple this theory to gravity. Right, that's right. So the extra terms that I didn't write down in the Lagrangian would contain something that looks like a mass for phi and other terms that break the shift and the Galilean symmetry. But the idea is that those are all suppressed, right, in this EFT power counting logic. They're suppressed by powers of M Planck because they come from the graviton loops, graviton corrections. Yeah, so that's the rationale for why they should be smaller than the other, irrelevant terms that we kept, because those other irrelevant terms are compatible with the symmetry. So it protects how they change under RG flow.
I mean, it could change, right?
But I think, the point, I guess, in both of our talks, right, is that sometimes there are a lot of extra conditions that come from the UV that aren't at all obvious from the point of view of just, is this a consistent EFT? So when I start writing down some light scalar field and try and construct the most relevant operators, that's me building a consistent EFT and then asking the question, okay, now what extra condition could I expect to derive from the UV? Which I think is like the program that we're both advocating.
I also have a question, but
Go ahead, you get priority.
yeah, okay. I was leaving other people to ask first. No, just very quick, Scott. I was not sure what are the examples you gave at the end. What are exactly the assumptions about the UV that you take? I mean, you talk about locality, unitarity, causality, but do you also assume that it's a weakly coupled description or all this rigid behavior that you were discussing? I mean, because I always thought that all these constraints always assume a weakly coupled description in the UV. Is that right? Or
yeah, that is right. Yeah, certainly for the second bound on alpha B and CT, when I showed this plot and I drew some green region, yeah, that is in the context of some weakly coupled UV completion. That's definitely true.
But that is not string theory necessarily, right? Because string theory, I mean, string perturbative theory is weakly coupled, but M theory is not weakly coupled.
Right.
So
yeah, so you can definitely access this, green region in perturbative string theory.
So
right.
it might be that the region of string theory is larger than what you
It might, yeah, right. I see. I think I understand your question. Yeah, if you have some non-perturbative corrections that, that violate some of these assumptions. No, that's a good. Yeah, that is a good point. I don't know. I guess I don't have too much to say about what happens for fully non-perturbative string theory.
Oh, I see Ted has a question. Go ahead, Ted.
Thank you. This is a question for Scott. I just wonder, the way you formulated the assumptions that you start with are analyticity properties of this function A of S. And I just wonder how important is it to really have that function defined on the entire complex plane? I mean, it seems like a huge assumption to say that it makes sense to talk about an amplitude for absolutely arbitrarily high, momentum or center of mass energy. And also that there exists even a continuous variable that measures such a thing, center of mass energy, in an unbounded way. Is it simply true that that really is like an unstated assumption that needs to be made to even state your assumptions?
Right. So I suppose the logic is that suppose that were true, that there were some object that you could define to arbitrarily high energies that tick these boxes that I mentioned. Then these EFT parameters would have to be positive. And so that argument in itself is quite rigorous, right? And how interesting you think that argument is, I guess, depends on how general you think those starting assumptions are. So if you think that in very few theories of quantum gravity, or not the theories that you're interested in, in theories that you're interested in, you think that there is no such high energy completion of the amplitude, then these bounds, would not apply in those cases. Or rather, if those bounds do apply, they don't follow from the sorts of arguments that I mentioned in the slides today. Right? Yeah, good. And that is definitely something that, that I think is super interesting, that I'd like to understand better and get input from people that work on quantum gravity from very different perspectives. So of course, as you can tell from the talk, I'm very much someone that thinks more about particle physics problems on a day-to-day basis than quantum gravity problems. Right, and so there, some BSM model, you're sort of very happy with the idea that you have some scattering amplitudes, and then when you UV complete it, you're just looking for some good, and so in cases like perturbative string theory, where we have some calculational control over what's going on, sort of see what's happening. But in other quantum gravity approaches, I think there's a lot less control. I don't really know exactly how you do this analytic continuation, but I think that would be very interesting. I'd be very interested to learn more about what the options are there, right? Because if it is possible to do this extension in your theory of quantum gravity, then there are very tight constraints on the resulting Eft coefficients. Right, so it's definitely worth exploring. Like, it's something to shoot for. If you can show that in your theory there is such a high energy object that ticks these boxes, right? Then that's you showing that your theory has very clear signatures in the IR, namely that these coefficients are bounded in this special way.
Do you think it's conceivable that you could generalize the arguments and get some non-trivial conclusion where you only assume something about A of S out to some radius in the complex plane or something like that?
Yeah, good. So, the reason I didn't mention these kinds of arguments, so sometimes you could imagine that there is some scale, Planckian or otherwise, up to which everything looks like a field theory, and beyond which things don't look like a field theory, and you violate these assumptions. And then when you try and derive these arguments, these ultimately follow from dispersion relation. You do complex analysis, basically. In the complex plane, you deform some contour integrals. And usually we send those contour integrals off to infinity. You have some circular arc, you send it off to infinity. If this object doesn't exist all the way out to infinity, then you can only expand your contour out to, let's say, the Planck scale. And then there's some contribution that you in principle should include in these arguments. So these bounds would not be that these coefficients are positive, but rather these coefficients are greater than this contribution to the contour integral that you're trying to do. Right. And it's tempting to say that, these things, because they all live at the Planck scale, maybe they're Planck suppressed. And yeah, those are arguments that sometimes I shy away from, just because of a lot of the things that Irene and others have mentioned, that there can be this UV-IR mixing that sometimes means that corrections that you would naively discard as small are actually important. So yeah, so typically when I think of it, I'm sort of imagining that these things are definitely true if you can extend this amplitude to high energies and close your contour really at infinity, where this Froissart boundedness argument lets you throw away that contribution to the contour. And you could imagine proving something similar if you had a finite contour that you couldn't extend to infinity, but then some stronger than Froissart bounded, something that told you that contour integral that you now have to keep is actually suppressed, it's Planck suppressed, for instance. That would be something you would have to show, I think.
Thanks.
Okay, let's take a final question from Steve and then wrap up. Go ahead, Steve.
Well, maybe to help out a little with that last discussion, but I also have a quick question. So, just having Lorentz invariance plus a very weak notion of locality is enough to basically argue you can go to infinite S, because essentially you can take a particle and boost it to get it to arbitrarily high momentum. And with a very weak notion of locality, you can do the same to one at the opposite end of the universe. And that's how you create a situation with, in principle, infinite center of mass energy. So it's pretty weak assumptions. Of course, you could violate them too, maybe by some, in some framework, but you don't need to assume that much beyond what we expect. And the question for Scott is, when you talk about models which lead to propagation of gravitational waves faster than the speed of light, I just wanted to be clear, that's only if you're realizing one of these Galilean models within string theory. It's not necessarily that string theory predicts that, but it's if you get a Galilean model like that out of string theory. Is that the correct statement?
Yeah, that's right. Because of time, I skipped over a slide that stated some of these assumptions. So yeah, those final phenomenological examples were all within the context of this particular scalar field theory. So you're imagining that your low energy degrees of freedom really are a metric, a scalar, and have those symmetries. Good. So there are some arguments that this final conclusion that gravitational waves should be superluminal. There are some arguments that might be more general. Okay, no one's proven that rigorously, right? So my claim here today was that in the context of this particular EFT, that's definitely what happens. It also happens if you just have GR as an EFT, so without the light scalar, if you just integrate out lots of matter fields and you flow down to the IR, in GR you have the Einstein-Hilbert term plus some higher derivative corrections, and it seems like those also push the speed of tensor modes on Lorentz-making backgrounds, make them superluminal. So those are kind of definitely two cases in which there is some evidence that this is what happens, but no one's shown that this is like a general that you're always going to land on superluminal gravitational waves.
Okay, thanks.
Okay, so I think we should wrap up. Let's thank Scott and Iren again one last time for the great talks and questions. And as a final advertisement, I'll remind everyone that if you'd like to continue these discussions, you can join the Slack channel. So Sebastian posted it in the Zoom chat, so you can go ahead and join there if you'd like. There's also a link I see to Scott and Iren's channel, or the channel for their talks. So we'd love for you to continue these discussions there. Otherwise, we'll see you next month for the next talk in the series. Thank you to everyone for joining, and have a great day, evening, whatever time it is, wherever you are.